This episode is brought to you by Cisco Educational Premium. Did you know that the Dirac equation is consistent with Schrodinger equation? In particle physics, the Dirac equation is a relativistic wave equation derived by the British physicist Paul Dirac in 1928. In its free form, or including electromagnetic interactions, it describes all the spin-off massive particles called the Dirac particles, such as electrons and quarks, for which parity is asymmetry. It is consistent with both the principles of quantum mechanics and the theory of special relativity, and was the first theory to account fully for special relativity in the context of quantum mechanics. It was validated by accounting for the fine structure of the hydrogen spectrum in a completely rigorous way. The equation also implied the existence of a new form of matter, antimatter, previously unsuspected and unobserved, and which was experimentally confirmed several years later. It also provided a theoretical justification for the introduction of several component wave functions in Pauli's phenomenological theory of spin. The wave functions in the Dirac theory are factors of four complex numbers, known as bispinors, two of which resemble the Pauli's wave function in the non-relativistic limit, in contrast to the Schrodinger equation, in which described the wave function of only one complex value. Moreover, in the limit of zero mass, the Dirac equation reduces the Wheel equation. Although Dirac did not at first fully appreciate the importance of these results, the entire explanation of spin as a consequence of the union of quantum mechanics and relativity, and the eventual discovery of the positron, represents one of the great triumphs of theoretical physics. This accomplishment has been described as fully on par with works of Newton, Maxwell, and Einstein before him. In the context of quantum field theory, the Dirac equation is reinterpreted to describe quantum fields corresponding to the spin-off particles. In its modern formulation of the field theory, the Dirac equation is written in terms of a Dirac spin-off field psi taking the values in a complex vector space described concretely as C4 defined on a flat spacetime Minkowski space R13. Its expression also contains gamma matrices and a parameter m greater than 0, interpreted as the mass as well as other physical constants. In terms of the field psi R13 C4, the Dirac equation evolved, and in natural units with Feynman / notation, the gamma matrices are a set of 4x4 complex matrices which satisfy the defining anti-commutation relations. These matrices can be realized explicitly under choice of representation. Two common choices are the Dirac representation, where sigma I are the Pauli matrices, and the chiral representation, the epsilon I are the same, but epsilon 0 is equivalent to the matrix 0, I2, I2, 0. The slash notation is a compact notation for A, the slash epsilon mu, A mu, where A is a 4-factor, often it is a 4-factor differential operator, partial mu. The summation over the index mu is implied. The Dirac adjoint of the spin-off field psi x is defined using the property of the gamma matrices, which follows straightforwardly from hemiscedastic properties of the epsilon mu. One can derive the adjoint Dirac equation by taking the Hamilton conjugate of the Dirac equation and multiplying on the right by epsilon 0, where the partial derivative acts from the right on psi by x, written in the usual way in terms of the left action the derivative, applying the I partial the slash plus m to the Dirac equation. That is, each component of the Dirac spin field satisfy the Gordon equation. Cisco Educational Premium is a section of Cisco Educational's with content that is not hosted here. There are episodes ranging from long to short videos. Remember those good old shots of ours? They are there. So do we get there? Use the link on screen or in the description or in the pinned comment below. Enjoy yourself. Now we'll see you in the next episode of Cisco Educationals.